This video on the Matrox Repixo FPGA development kit is the first of two on the Vivado HLS design flow. We will use the provided HLS code examples to create fully optimized processing units, with code development and hardware simulation done in Microsoft Visual Studio, an environment already familiar to software engineers. When the code is working in simulation, the Vivado HLS IDE is used to compile it for hardware and to package it as IP compatible with Vivado IP Integrator. In the FDK install directory, you will find an examples folder. The HLS examples include several different processing units, plus an include folder with common header files. The simplest example is add constant. The files used by each example use a particular naming convention which you can read about in the FDK user guide. Here in Chapter 5, there's a full description of all the different files involved in each example. Note that this file, which ends in _hw.cpp, is the only one containing code that will be compiled for the FPGA. There are also one or more folders containing a Visual Studio project for the main mill application. There is a Visual Studio project you can use if you don't have mill installed on your computer. And the folder ending in _prj contains a Vivado HLS project for compiling the HLS code into hardware. Now let's open the Add Constant project in Visual Studio. This is the main program which allocates buffers, loads an image from disk and displays it, calls the custom function, and then calls it a few more times to measure the processing time, and finally it checks the output against the known good result. The HLS code that does the actual processing is in this file. We will look at that code in detail in a later video. Before we run the program, let's make sure we are using it in simulation mode. In this header file, when C2H debug is not defined, the real PU will be used in the FPGA. In this case, C2H debug is defined, so the HLS code will run on the host CPU to simulate the FPGA. Now compile and run the code and see what happens. The original image is displayed, and when you press enter, it will be replaced by the processed image. Notice how the result image is brighter because a constant value was added. The result was also validated and all pixels are correct. Now that the HLS code is working in simulation, the next step is to bring it into the Vivado HLS IDE and compile it for hardware. This is a process known as C synthesis. To open the Vivado HLS project, first locate the project folder. Then double-click the APP file to open the Vivado HLS IDE. In Vivado HLS, the only file we really need is the hardware.cpp file. Make sure that this file is selected for synthesis in the project settings. Here we can see the name of the file that will be compiled. Also, the top function must be the name of our HLS function. Remember that this file is the same C source code that we just validated in Visual Studio, so we are ready to run C synthesis. To run C synthesis, either select it from the menu under Solution, or press this button. Synthesis takes a few seconds and displays a report when it finishes. In the Console tab, we can see that C synthesis has finished. And in the window above, here's the report. Under timing, the clock period target was 4 nanoseconds, and we achieved 3.44 nanoseconds. This means that there will be no timing-related problems. If we expand the loop section, we can see that the X loop was fully pipelined with an initiation interval of 1 cycle. This is the most important indicator that the function will reach the intended performance in the FPGA. There is also a table with resource usage estimates. This is especially useful for complex functions where you need to optimize resources in order to fit in the available space. Since everything looks good in the synthesis report, we can now run the last step, which is export RTL. This button performs the RTL export. Make sure the format selected is IP catalog, and then press OK. In the Console tab, we can see that Export RTL has finished. This process packages all the generated files ready for use in IP Integrator. To locate the packaged IP, start from the project folder and then navigate as follows. First, navigate to Solution 1, then Implementation, and then IP. This is where all the generated files are found, and the ones that we actually need are in this zip file. Later, we are going to use the generated IP for add constant and the other example PUs in IP Integrator to make a new block design. But first, we have to generate the IP for the other examples. This means opening each Vivado HLS project in turn, running C synthesis and export RTL, and generating the zip files containing the IP. The other examples are convolve, gain offset, and min-max. You can ignore add constant for now. You will need the IP for each of these functions if you want to follow along with part 2 of this video. The topics covered in this video are described in more detail in the FDK user guide. It's also important to read the Xilinx Vivado HLS documentation, especially UG902, the HLS user guide. Also watch part 2 of the HLS design flow video where we produce custom firmware containing the example PUs and test that firmware by programming the PUs with the MIL MFPGA functions.